Today's lesson is about a concept called the dot product. This is one of those concepts that's deceptively simple, yet shows up absolutely everywhere in physics, computer graphics, engineering, and of course, here in our calculus and vectors course. Have you ever wondered how a computer figures out how bright a surface should be when a light hits it? Or how an engineer checks whether two forces are working together or against one another? Or how a game engine knows when two objects are aligned? All of that uses what we call the dot product. So far, we've learned how to represent vectors geometrically with arrows and algebraically with components. We know how to add, subtract, and scale them using those scalar multiplication things that we did last time. But now we need something new. We need a way to combine two vectors to get a single number, a scalar, that tells us something meaningful about how those vectors relate to each other. So what are we going to talk about today? Well, we're going to talk about this dot product geometrically. We're going to talk about the dot product algebraically, and then we're going to look at how they connect to answer some real-world problems. So we already know when forces act on an angle. Some of that force acts in the x direction to move the object forward, and some of that force acts in the y direction. We've already talked about this, but it's worth mentioning again because it is a concept that we're going to use today. So let's look at this particular question and let's determine the horizontal component of the vector shown. So I have a vector, and here it is. I'm going to highlight it in red. That's acting, it's 30 newtons of force that's acting at a 40-degree angle to the horizontal. So remember, if I want to know the horizontal component of this, I am taking, if this is my total force, my force vector, then my x component of this, so my fx, will be equal to the magnitude of my force component times cosine of the angle theta. So in this case, that would be f at x is equal to, we're going to fill in some numbers, 30 newtons times cosine of 40 degrees. Now, we could go further and we could continue to do the math on this, which I actually haven't done yet. So I'm going to pull out my calculator. So we have, oops, not that. Here we go. So we have cos of 40, and we're going to multiply that by our force of 30, and so that gives us a force in the x direction of 22.98 newtons, and I would round that up to 23 newtons just given that we only have really I'd probably round it to 20, but for what we're doing here in math, I'm going to round it to 23 newtons just given that we have two digits in each one of our values. So did you know that we can actually use another method that's not like this at all? Well, it's kind of like it, but a little different. But we can use another method to determine how much of the force vector acts in the x direction and how that actually impacts what's happening in the x direction. This is where the dot product of geometric vectors comes in. I know I said we were leaving geometric vectors behind because they're messy, but we're going to use them here to help understand what the dot product actually is and what's happening with the dot product before we apply it to algebraic vectors. Okay, so when we're talking about this dot product of two vectors, let's say we have vector A and vector B, and they've been placed tail to tail. So here they are. Here's vector A coming up this way. Here's vector B. Oh, we can't even see all of vector B. Here's vector B in the blue going along in this direction. So we've got two vectors. They've been placed tail to tail. And there's some angle in between them. So what does the dot product do? Well, it actually tells us how much the two vectors are working together. It's like asking how much of vector A is going in the same direction as vector B. And we can see and we know that only the x component of vector A in this case is going in the same direction as vector B, which means we're only going to use that x component, or the magnitude of A times cosine of that angle. And that's really what this is saying here. So in mathy speak, we can define the dot product as the following. So for two vectors, vector A and vector B, the dot product is defined as vector A dot vector B. That's how we refer to this. It's not multiplication in this case, and I know sometimes in math we use a dot to represent multiplication, but the dot product isn't actually just straight multiplication. So we will say vector A dot vector B is equal to the magnitude of A times the magnitude of B times cosine of theta. The order of that magnitude of A and B doesn't matter at all. A times B and B times A are the same thing. Theta is that angle between the two vectors when the vectors are arranged tail to tail, and that angle really needs to be between 0 and 180 degrees. The dot product is a scalar quantity, and that means that it gives us a scalar product only. It has magnitude but no direction, and the units depend on what we're doing with it. So it depends on the application, and there's lots of different ways that we can use this geometric dot product, but we're going to look at one that I think most of you will be familiar with. So in physics, a great application of the dot product is to calculate how much mechanical work is being done on an object. Now, work, for those of you that aren't familiar, is the product of the magnitude of the displacement, so the distance traveled in a direction, so the distance traveled by an object, and the magnitude of the force that's applied in that direction of motion. Now, this dot product and work is again, I've said this already, is a scalar product. So we're going to use the equation of work is equal to that force times the displacement or the distance of the object. So the force here is measured in a unit called newtons. So this is in newtons. And the displacement is usually measured in meters. And that's going to give us a unit for work that's going to be in Newton meters, but the actual unit of Newton meters is a unit called joules. And we abbreviate that with a capital J, and it's actually named after a man named James Joule, who actually is the father of modern day thermodynamics. He did a lot of work with heat transfer. So any of you that have taken physics have probably heard of him. Okay, so we know that work is equal to the force in newtons times the displacement in meters. So let's try a question. So if a 30 Newton force is applied at an angle of 40 degrees to the horizontal to move an object 5 meters, how much work is done? Well, I've already given you a bit of a drawing here. It is important to do a drawing just so you know what you're working with, and it kind of can put the question into a bit more context. So what do we know? Well, we know that our force vector is equal to 30 newtons, but remember the magnitude of the force that we're concerning ourselves with here is only the force in the x direction, so it's 30 times cosine of that angle 40 degrees. The distance or displacement that we're dealing with, because displacement is a vector, it has direction. The displacement is 5 meters. And I got that just right from the question, so no math required. So if we want to calculate how much work is being done, remember, it's the magnitude of the force times the magnitude of the displacement. I'm going to write that a little bit differently. I'm going to write it more in terms of physics for right now, and then we'll look at why this works in a second. So work we know is equal to force times the displacement. Now, our force we know is equal to this. So we have 30 cos 40 degrees times my displacement, which in this case is 5 meters. So this gives us a total amount of work that's been done of approximately, 114.9 Newton meters. Now remember I said the unit for work is actually joules, so we're going to round that up to 115 joules of work being done to move this object 5 meters when a 30 Newton force is applied at 40 degrees. Now, it wouldn't matter how we do this one. We could do it like we did it here, where we took the x component of force and multiplied it, or we could take 30 times 5 times cos of 40, because it all equals the same thing. Okay, so this is what I was talking about when I said it really doesn't matter how we write these out. So in general, we can think of this work being done as equal to the magnitude of the force times the magnitude of the displacement times cosine of theta, where theta is the angle between the two vectors. In general, we can use this for any two vectors really that are tail to tail. So u dot v, or vector u dot vector v, is going to be equal to the magnitude of vector u times the magnitude of vector v times cosine of the angle in between them. So let's try this one. No diagram required this time. Let's just work with some numbers. So given that the magnitude of vector u is equal to 4, the magnitude of vector v is equal to 6, and there's an angle between them of 26 degrees, find u dot v. So I want you to pause the video and give this one a try, and then come on back and see if you got the right answer. I think you're seeing this is pretty basic math compared to some of the things that we have been doing. So vector u dot vector v, see, I do it sometimes too. Vector u dot vector v is going to be equal to u, the magnitude of u times the magnitude of v, cosine of the angle. So the magnitude of vector u is 4. So we have 4 times the magnitude of vector v, which is 6, times cosine of the angle, which is 26 degrees. When we do that math, the amount, so the amount that they work together, I guess, is the way to talk about this. The amount that these work together has a magnitude of 21.57. No units here because we don't have units in this particular question. We don't know if this is force and distance or what this happens to be. Okay, so here's some properties of this dot product that you should be familiar with. So the first one that we have is this idea here that vector u dot vector v will be equal to vector v dot vector u. We call this the commutative property. So this is the commutative property. It doesn't matter if I have u dot v or v dot u, the product of that will be the same. That's the same as in regular math. It doesn't matter if I have 1 times 4 or 4 times 1, it's all going to just equal 4. The second one that we have here says if I have some scalar, k, times vector u, and I dot that to vector v, well, that's going to be equal to vector u by itself, dot now k times vector v, and that whole thing can be equal to k times u dot v. This is what we call the associative property. This is the associative property. So the dot product isn't associative like normal multiplication. You can't dot your way across multiple vectors, but you can multiply a vector by a number or scalar before or after dotting, and you'll get the same result. So whether I multiply it before I've dotted it or I multiply it after I've dotted it, I'm going to get the same answer. The last one here is the distributive property, and we're used to that one from algebra. The distributive property. Now, the distributive property for the dot product behaves the same as with regular numbers. You can distribute the dot product across the sum just like in algebra. So if I have u dot v plus w, that's the same as saying, like I'm distributing this in here, and now I end up with u dot v plus u dot w. The answers will be the same. So let's look at a couple of examples here and just think about what we've got going on. So determine the dot of u dot u. So determine the product of u dot u. Well, u dot u, they're both just the same vector. So they're probably on top of each other. They're going to multiply together. We would say they're collinear. They have no angle between them. So they're likely just right on top of each other. They're the same vector. So we would say that u dot u is equal to the magnitude of u times the magnitude of u. Because remember, we're still using that same formula, times cosine of the angle 0. So this time we have an angle of 0. Now, cosine of 0, remember, is just equal to 1. So we really end up with the magnitude of u squared. So if I am crossing two vectors that are identical, that are collinear to one another, they are equal to just the magnitude of that vector squared. Now, let's determine if u dot v, if vector u is perpendicular to vector v. So they're perpendicular to each other. That means there's an angle of 90 degrees. This you may find referred to in your textbook as orthogonal, just means 90 degrees. So anytime you see anything that says it's orthogonal, just know that it's 90 degrees. So let's think about this one now. So we know we're going to have the magnitude of vector u times the magnitude of vector v, and that's going to be times cosine. This time our angle is 90 degrees. Now, the cosine of 90 is actually equal to 0. So that means that our dot product of u dot v is actually going to be just equal to 0. So a few important properties there. Here is an actual breakdown. Sorry, I just got to move my papers here. Oh, and I'm turning things sideways. Hold on here. Okay, so here's a breakdown of all the properties of the dot product. This is from your textbook. You can pause it and have a read through it here. It basically is what I just told you, only in a little bit more mathy terms. So remember I said that we actually were going to take what we knew about what was happening in geometric dot product and apply it to the dot product for Cartesian vectors. And that's what we're going to look at right now. So in this form, so in Cartesian form, we know that we have two coordinates, an x and y coordinate for each one of our vectors. We know that they start at the origin. So in this form, the dot product is actually easy to find because we know the x and y components of each vector. If we want to find the dot product of two vectors to get the scalar product, all we have to do is multiply the x components of the vector plus the product of the y components of the vector. So what does this look like? Well, if my vector u has 2 points, or has two coordinates, u1 and u2, and vector v has two coordinates, v1 and v2, then the dot product of u dot v is simply equal to u1 times v1, or the product of the x components, plus the product u2 times v2 of the y components. Now, we can actually also use this same concept in 3-space or in 3D. We're going to talk about that in more detail in another lesson, but I just thought you should see it. And this is what I was talking about when I was saying that it is actually easier to work with vectors in Cartesian or algebraic form when we start getting into higher order spaces. So when we have 3-space, you can see that I can still dot them. I can still find the product of them, and it just becomes the product of the first, or this would be our x values, plus the product of our y values. And then we also have to add the product of that third dimension. That would be the dimension z. Like I say, we're going to leave that. So that's 3-space or 3D. We're going to leave that for a little bit and come back to it in a couple of lessons. Okay, so let's look at one final example. So if I give you the vectors, if we're given vector u is equal to 5, negative 3, and vector v is equal to 4, 7, let's determine u dot v. So remember, just given what we've got right here, u dot v is going to be u1 times v1 plus u2 v2. And just given our numbers here, we can start plugging things in. That's 5 times 4. So I've got u1 v1 plus u2, which is negative 3, times v2, which is 7. If we go ahead and just do that math, we get an answer of negative 1. So the amount that these two work together is, in this case, negative 1. Okay, so that's everything for today. Hopefully, a little bit of a shorter lesson. Hopefully, a little bit easier maybe to understand than what we were talking about yesterday. Not a whole lot of homework tonight, just a few questions from the textbook. And for the next lesson, we're going to take this dot product and we're going to apply it to some other situations. And that's where we're going to start to see the beauty of the dot product, is when we start actually not just using it as a concept to get the product of two vectors, but we're actually going to be applying it and putting it to some applications. As always, if you have any questions, feel free to send me an email.